Hi, hello, and welcome. Section number 8. Woot, woot. After this, only 2 more sections. Gasp. Sad. Y'all are almost done. This week for class, just lecture-wise, so you know when you're prepared, is like a fire hose week. Like last week was its kind of own thing with the GFP, and then lecture 7 was like more SN1, SN2 revisited. This is like reactions, like just throwing at you. So being on that study train of getting those reaction basics down, try the desert island exercises, which I keep plugging for people. I find them very effective, but that's just me. Mid-semester meetings are happening. Thank you so much. I've loved like meeting with people so far, and I have more meetings today. There are still open slots, so if you have not signed up for a meeting, please sign up for one. And then, several people, this QR code, in our meetings, they're like, but what about the grade? And this is just like a spreadsheet that I made that uses the values from the syllabus that anyone could do. But it's just a spreadsheet since many people ask about it. And again, themed QR code percentage. Ooh. We have some memes for you today. There was one section where I still don't have any memes. Maybe it was section 7. So I don't know if anyone noticed or cared. I'm still going through all the feedback because there's a lot. But overall, y'all were very, very sweet. My God, thank you. And in terms of like figuring out some like things and logistics and suggestions, one of them is like section videos being posted faster, which like, yes, would love. They're just like very big file sizes. Like, and so especially if I'm going out of town, like Friday through Sunday, I don't really have an opportunity to upload them immediately. But all of the 2024 videos are like fully on Canvas, ready to go, and they're pretty similar. So, like, I would say if you're ever waiting on me, just watch that instead, and you'll get virtually the same thing. In terms of, like, what to do in section, the thing is, it's so mixed what people want. Like, some people... I was surprised by how many people said section should be 2 hours. I said, are you sure about that? Are you really sure about that? But some people want like harder questions in section, and some people are like, oh, I like the kind of building the skills foundations so I can do the harder ones later. Some people want more time to work. Some people want no time to work and just want guided problems, and like they're like, it's a waste of time giving me 3 minutes to work here. And I'm like, that's what I do. like everyone kind of wants kind of different things. And so I'm going to go through, I'm going to try to do like summations and get like a tally and see like, is there a majority one way or the other? But it feels very in the middle just from like reading through it so far. So we are out here. Yeah. Okay. So we have reached lecture 8. We've reached the wheel. My heart and joy, my pride and my prejudice. Here we are. So this is my favorite thing that I've made for this class. It summarizes all of the reactions. The goal for today is to try to get a handle on alkene things. We're not going to touch radicals yet. Radicals will be in section 9. But just because, like, again, it's like a big torrent of reactions that was thrown at you yesterday, one thing that I want to try to do is help kind of organize and scaffold it a little bit. So it didn't exactly line up with exactly half down the middle, but I would call these red, purple, and blue ones, everything on the right here, I refer to them as the simple alkene additions. So these simple reactions are ones that are primarily mechanism tested. You will need to know the things like the red family uses carbocations, the purple family does the little cyclic bromonium, and then the blue family does like alcohol things. But then the other ones I refer to on the left side over here as the complex alkene additions. And they're the ones where the mechanisms are a little bit weird. And to be so honest, we are probably not going to ask you about any of the mechanisms for the ones on the left side here. So all of these mechanisms are just kind of like vibes. The one exception is radicals, which we'll talk about again in section 9. But like, for example, if we did a mechanism question with MCPBA, love her, she's great. It's a one-step mechanism. So what would we do? Like, I mean, I guess it could be part of like a multi-step like mechanism. but like you're much more often going to be seeing the left side of these as line reactions and synthesis, and the right side of it as mechanism, theory kind of things. Then also the families are grouped together by similar mechanisms. So there is indeed, if you'll notice, a color ombre, where like all the ones that are in the same color here have very similar mechanisms of action. So just to kind of help put some of the patterns into perspective. But the wheel here is great for kind of visually laying it out and seeing it and having one reference. But let's talk a little bit about some like alkene terminology to kind of ground us as to what we should be on the lookout, high alert for with alkene reactions. So we have 3 logistic questions that we have to answer with every alkene reaction. What, where, and how. The what. So whenever we have an alkene reacting, we are adding 2 things to it, one on either side of the double bond, so to each carbon. And you need to know what are the 2 things that it adds. For example, this reaction with H3O plus adds an OH and an H. This reaction with like a dihalide and an alcohol adds an alcohol and a halide. So the what is just what are the 2 things added. The where is a question of regiochemistry. Regiochemistry, like what region of the molecule is reacting. And most of the regiochemistry for the alkene additions follows Markovnikov's rule, which is the more electronegative thing adds to the more substituted side. If you look at like other resources for alkene reactions, they might phrase this rule slightly differently. Some say like the hydrogen adds to the least substituted side. And there are like 2 or 3 other ways that you can kind of word it, but we like more electronegative, more substituted side. And the more electronegative thing is typically the thing that's the nucleophile, and the less electronegative thing is typically a hydrogen for a lot of the reactions. So here, when I say more substituted side, which side is more substituted, 1 or 2? 1. And what I mean by that is how many non-hydrogen things are already on it. So this side has 1 non-hydrogen thing, this other side has no non-hydrogen things. So this side is going to be more substituted. So Markovnikov's rule, we would add our nucleophile, more electronegative thing, to that more substituted side. However, sometimes we are going to intentionally want, for the sake of synthesis, for certain molecules that we're building, we're going to want to add things to the less substituted side, our nucleophile to the less substituted side. And we call that the anti-Markovnikov product. So for this, each of the stereochemistry here, Markovnikov, 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 anti-Markovnikov, Markovnikov, Markovnikov, it's kind of duck, goosey. But like the what, where, and how for all of these reactions I've kind of listed up here. So the last question, the how, it's really like what is the relative orientation of the 2 things added? So let's say this is the double bond here. It's like the arms. If 2 things add to the same side, like both up, or if the 2 things add both down, then we say it's syn on the same side. If one of them adds up, one of them adds down, or vice versa, one adds down, one adds up, it's anti. And so we're going to do the syn and anti dance, which is syn, syn, anti, anti. Can we do that? 1, 2, ready, go. Syn, syn, anti, anti. Ding dong. Walk around campus. Keep on doing it. Indoctrinate people into it. It can be the Camp Rock. I don't know the thing that they do, but you know the thing that they do. Maybe. But yeah, syn, syn, anti, anti. Just walking around the streets of Harvard Square.
Oh. Like, it kind of strange that some of them say like syn and then anti-Markov.
Oh, I'm getting there. Warning. Anti-stereochemistry is not anti-Markovnikov. Not all antis are created equal. So it's something that you have to watch out for. Are we talking about anti in terms of anti-not Markovnikov? Or are we talking about anti in terms of Blanc, the stereochemistry? So I've put some like figures here to kind of see it a little bit, and here you can visualize the syn as being like both dashes, both wedges, or you can view them kind of stereochemistry as like up or down. And same here with the anti. But then some reactions are not selective for syn or anti. And so we would say it's a mixed orientation between them. So especially these first family that we talk about, they're going to be all mixed, and it's because they have carbocations. But then all of the ones with a dihalide, all of these are anti-additions. That's kind of a classic characteristic of them. And then each of the other ones, they have their own patterns regarding it. Work. Now, we have this stereochemistry question of the how, which is only really relevant if we are forming stereocenters. If we are not forming stereocenters, our lives become so much easier. Like, look at this. If I did this reaction, I added two things, R1, R2. Is this a stereocenter? No, we have two methyls. Is this a stereocenter? No, we have two hydrogens. So, like, this is the nice version. We also want to be prepared for the horrible, rotted, gutted version. But let's start here. So, any questions about the three logistic things that you need to know for all the alkene reactions of the what two things are added, where are they added, Markovnikov or anti-Markovnikov, and how are they added, syn, anti, or mixed? Maybe I need a little move for mixed. What would mixed be? Mixed. Yeah, Ava. Yeah. Work. Okay, we'll try it out. Bless you. So let's jump on, and the structure of the next section is we are going to talk about each of these little families, and then after we talk about the family, we're going to do a little practice, and the little family and the little practice. So first off, let's talk about our first group, which I call the acid additions. The basic mechanism of all of these ones in this kind of red family are an alkene is reacting with some sort of acid. So it could be like HBr, it could be HCl, or it could be like H3O plus, where this is an H on an OH2 plus, and like that's our acid. It could be acid and an alcohol, in which case this would be HOR plus protonated. But either way, the first step you could even draw just as H plus, but I like to list out all the options to kind of notice some of the patterns. First step is the alkene grabs a proton, and then we have two choices. We can either add the hydrogen on the right side or the left side. Which do you think we want to do based on these carbocations? The right side here. When we do that, what type of carbocation is this? Primary, secondary, or tertiary? Secondary. What's the option over here? Primary. Which one's more stable? Carbocation experts out here. Really, really knowing the game. I see you. So we are indeed going to form this one and not this one at all. So we have our more stable carbocation. And I will say this image is a little misleading because it does not match up with this molecule, which I'm just noticing now. But it's still the same argument. It's just now this is a tertiary carbocation for this specific example. So apologies about that. Now, once you have the carbocation, then the second step is just whatever the other thing that's present, be it the Cl, the Br, the water, the alcohol, goes and attacks the carbocation. And then you have added two things where your carbon-carbon double bond was. You might have to do a final deprotonation step to make it neutral, but this is the kind of like basics of it. Now, when you form a carbocation, you always have the potential for rearrangement, so watch out. Let's talk about the gross part. So imagine we have this horrible, horrible molecule. And does everyone remember what D is? Deuterium. That's the isotope of hydrogen. It's just like a labeled version of hydrogen, essentially. So if we do our first step, where we are adding a proton here, which side are we going to add the hydrogen to? Well, if we add the hydrogen over here, then that makes a tertiary carbocation. If we add it over here, it looks kind of tertiary, but it's really only secondary. Because remember, deuterium is just like a hydrogen. So the one that's more stable is to make our carbocation up top. But, wow. We actually get two options when our alkene goes and grabs a proton. So the first option is if our double bond's here, we could have grabbed a proton from the top face of this double bond. In which case, our hydrogen would be added on a wedge over here. Or we could have had our double bond and grabbed a proton from the bottom face over here, and then it's added on a dash. And both are going to happen. We can't control it. So that's the first point where we get like divergence of our stereochemistry things. But then, remember when we talked about SN1 reactions, where we had an MTP orbital and a nucleophile came and attacked it? It could attack the top lobe of that, or it could attack the bottom lobe. So what we're going to get is, when we add our nucleophile over here, we get sometimes the nucleophile adds on a wedge from the top face, sometimes it adds on a dash from the bottom face. And same thing over here for this carbocation. So what you get is like a whole smorgasbord of products. You get 4 different diastereomers formed from this reaction. Horrible. Gutted. And like, we could ask you to draw all of them. If we did ask you to draw all the products formed for something like this where there are lots of stereocenters, the easier way to do it is you could just draw one batch of it and then use the plus minus to say that we have the enantiomer. So if we remember our definitions of enantiomers, one way that we can define it is that all the stereocenters swap, right? So let's say I just wanted to draw these 2 structures. If I put a plus minus with this, that indicates that I also have the enantiomer of it where both of them are in wedges. So I don't have to explicitly draw this if I put a plus minus. Similarly over here for this one, if I like swap the wedges and dashes, I get this one over here. So I could answer this question fully just by writing these 2 structures with plus minus for each of them. But it's really annoying. I'm so sorry. And again, this will mostly be kind of an infographic to go back to and like check your understanding of the stereochemistry. It's going to be much harder than most of the questions that we will ask about these reactions. Typically, there will only be like 1 stereocenter. But also because of this carbocation here, we're going to get a mixture of the syn product and the anti product. So we're not selective of syn versus anti for our stereochemistry. Now, the rearrangement things to watch out for. So if we went and grabbed a proton here, made this secondary carbocation, it's adjacent to a quaternary carbon. We can still have rearrangements like our methyl shifts or hydride shifts, things like that. And so we are going to get products that may have funky things happening. Yes, just something to watch out for. Here are the like 4 reactions in total for this family. You have the HBr and HCl versions. In these, you add an H and a Br, or an H and a Cl. And then in the alcohol and water versions, you add an H and an OH, and an H and an OR. And oh my gosh, we found another sneaky way of making esters. Ding dong. So this is kind of a basic setup for the acid additions. Why don't you try out a question where you are going to be looking at some of the stereochemistry here of the products. So this is just one that I made. There are 2 alkenes here, and I want you to try drawing all of the possible products of the given reaction. I remembered to unmute my mic this time, so that's good. So, drawing all the possible products of the given reaction, one thing I like to do for alkene reactions, just as a reminder for me, is do my logistics questions before I even start writing anything. So if H3O plus is on the arrow, what are the two things I'm adding to an alkene?
H and OH.
There we go, H and OH. Now, is it Markovnikov or anti-Markovnikov? Markovnikov. And again, these are key features of just the reaction that you will learn and memorize about the reaction. It's always going to be the same answers for these. So it's going to be Markovnikov. Oh, where is she? There she is. Mark. And then is she going to be syn, anti, or mixed? Mixed. Okay, so first thing, let's draw the carbocation, because that can get us into trouble if we do not think about the carbocation, potential rearrangements, and everything. So we are going to form the carbocation here, and we're going to have the hydrogen on the less substituted side of our double bond. Is that carbocation going to rearrange? No. If there was no methyl here, is that carbocation going to rearrange? Yes. So that's why I think it's helpful just to visualize the carbocation, even if you know what's going on, because otherwise you can miss an easy rearrangement on the test. Okay. And then also, is this a stereocenter? She has another hydrogen already there, so she's not a stereocenter. So that makes our life easier. We're not going to get 4 separate products because there's no stereocenter there. So, we have one version where our OH is going to add on a wedge. It'll add from kind of the top face of this MTP orbital. And we also have the enantiomer, which I'm just going to do as plus minus. So that's the version where the OH is on a wedge and this is on a dash. I said the exact wrong things, didn't I? The enantiomer is the version where the OH is on a dash and the tert-butyl is on a wedge. So we can draw it like this, or we can draw the separate structure. I typically try to choose the path of least resistance. So, cool. So let's think about questions on this one. Yeah.
So I did this, but it doesn't mirror what you did. I don't know.
So yeah, there shouldn't be a wedge or a dash on this line because that's the basis that you're comparing it. But then what you did was you just drew an H here on a wedge or a dash, but that's not a stereocenter, so we don't care. Yeah. Yeah. Okay, so then for the second one, HCl, what two things does it add? An H and a Cl. Yeah. Then anti-Markovnikov, Markovnikov. She's Mark. And then syn, anti, or mixed? Mixed. Same for all of the ones in this family. We will do our carbocation just to keep us honest. Now remember, the deuterium is like a hydrogen, so we are going to want to make the carbocation over here in this tertiary position, and then we add the hydrogen here. Now is this a stereocenter? Yes, she is, because the deuterium and hydrogen are technically separate things. So we're going to get a version of this where our hydrogen is on a wedge, deuterium's on a dash, and vice versa. So let me go ahead and start drawing that, because this seems like the version where we're going to get multiple stereocenters. So one version, my hydrogen's on a wedge, deuterium's on a dash. Another version, my deuterium's on a wedge, and my hydrogen's on a dash. And then, is this carbocation going to rearrange at all? No, it's tertiary. It's always as stable as it's going to be. So then, on the other carbon, we need to add the Cl. And the other thing that we have is the methyl. So if the Cl adds from the top face, then the methyl is going to be on the bottom face. So Cl would be on a wedge, methyl would be on a dash. So that's one version. Cl is a wedge, and methyl is a dash. But then if we think about the other version of it, where Cl is on the dash and then methyl is on the wedge. We really just need to make sure that we get the 4 combinations of all the wedges and dashes, right? So what I'm going to do over here is I'm going to look at actually the 2 things I added, the H and the Cl. And in this orientation, are they syn or anti? Syn, they're both on wedges here. So over here in this version, I need to draw it the anti version. So here, if the H is on a dash already, I'm going to draw my Cl on a wedge. And the methyl on the dash, just the same. So it looks like I'm doing the same thing, but it's because I haven't accounted for the enantiomers of these yet. And I'm going to write +/- for both of these. And so with that, we get the version where these are added both on wedges. We get the version with the +- where these are added both on dashes. And we get both of the anti-combinations, where 1 dash and 1 wedge, and then 1 wedge and 1 dash. Yeah.
But if you were to rotate let's say the right side of the molecule around that carbon, then
Okay.
wouldn't you get a different wedge and dash thing that can account for an
Yeah.
number, but it's the same thing?
Totally. Just in the same way, remember we were doing the 1, 2, 3, 4, and we talked about all the different ways. Yeah, there are 4 or 5 different valid ways that you can write any scenario center. So as long as you have all the options, great. Go with God.
Okay, so just because you can write it in a different way and it's the same molecule doesn't mean that it's redundant as an answer.
No, I just be sure of yourself in terms of make sure you're not just drawing the same molecule twice. Or make sure that if you're using this plus and minus, one thing that would be wrong is if I wrote this up here in the plus minus, and then the second structure I drew was so if I drew this as the second structure with a plus minus, the reason why this isn't going to be the wrong answer is because these two are enantiomers of each other. These two had an all swap. So I have just drawn 2 of the products total because these 2 are representing the same thing. I totally lose everyone with that. I feel like it's getting so in the weeds with the stereochemistry. Let's see. This is the hardest stereochemistry, I think, of the lecture. So it does not get worse than this. Yeah.
So could you add wedge on the ethyl rather than methyl? Why did you decide to put it?
I just decided. Yeah, no, you could add it on either one. Just as long as you get all the combinations of wedges and dashes for this. You should be good. Cool. So, let's transition to another family. So, what? No, that's RuPaul's Drag Race. Diners, Drives, and or what is it? I don't know. Thank you. Yeah, no, it was in fact RuPaul. But next up, we have the halogen anti-additions. And we do see the word anti in its name. So what do you want to guess the stereochemistry of this is? So the mechanism for this, it's very fundamentally different than the carbocation one. The carbocation one, normally you grab a proton, make a carbocation, blah. This is, the double bond is going to go out and attack a halogen. And specifically, we are doing the pi CC attacking the sigma star dihalide. And then you are going to have the lone pair on the halogen attacking back to the pi star CC. So what it does is this kind of concerted reaction where you are making a bond here. We put electrons in the antibonding orbital, so we have to break that bond. That's kind of a consequence arrow. And then it's attacking right back and making another bond, which breaks the pi bond, which is doing the attacking. Oh my gosh, concerted. It drives itself forward. So with this, we wind up with a cyclic bromonium or cyclic chloronium ion, depending on if we have a bromine or a chlorine. And again, we have 2 options here. If our double bond's this way, we could form a little triangle going up, in which case they're both on wedges, or we can form our little triangle going down, in which case they're both on dashes. Now, once we form this, and she, again, looks like our epoxide girl from last time. Epoxide in acid was the type where we said that the nucleophile added on the more substituted side, and in acids where it had the positive charge on it. But when we have a halogen with 2 bonds, she has a positive charge. She behaves very, very similarly. Our nucleophile is going to attack the more substituted side in both cases. But we don't get a total of like 4 options for this. And it's because if our like bond is on a wedge here going up in the plane, then we know the antibond has to be below the molecule. It's kind of like what we saw in section 7 with epoxide things of, here, imagine that this is the bromine with a positive charge. If it's on wedges going up, the nucleophile has to attack from the bottom. So it's not like the carbocation where it could attack from either face. So because of that attacking from the bottom when it's up on a wedge, we get specifically only anti-products, where our halide and whatever our other nucleophile is are added one on a wedge, one on a dash, anti to each other. Now, the classic flavors of it are Cl2Br2, and what they add are just 2 Brs or 2 Cls. But, of course, there are more flavors. So, over here, if we do our halogen reaction in water, we form our cyclic bromonium ion, and then this is what it looks like. Who do you think is going to win? One bromo boy or a bunch of water? Water! And it's not that water is a better nucleophile, it's just like more abundant. So what's going to happen is, in this case, a water is going to come in and do the backside attack here. And so the second thing that we add after the bromine is going to be an OH. And there will have to be a deprotonation step to make it neutral. Same thing over here for Cl2. We would add Cl, and then we would add an OH. And then we can do the same thing with, imagine instead of H2O, we have alcohols. So if these were all ROH, 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 you get the picture. Who wins? One bromo boy or all the ROHs? ROHs. So in that case, what adds? We have a bromine and then an OH or an OR? OR. It's really hard to break a carbon-oxygen bond. It's not hard to break an oxygen-hydrogen bond. And so we have found another way of making an ether. They're everywhere. Ethers, I hate them. Yeah, least favorite functional group. So specifically, these also have like fancy names, because now that we're not just adding a hydrogen, we have 2 functional groups on like adjacent carbons here. So we have vicinal dibromides. They're bromides, 2 of them. They're in the same vicinity. They're neighbors. We have halohydrons, which, what did we remember about halohydrons from last lecture? She makes epoxides. So now we can go from an alkene to a halohydron to an epoxide if we wanted. Or we could go directly to an epoxide. There are lots of options. Isn't it great? Aren't you so glad you know this? And then over here, we get a halo ether. I don't know. It reminds me of like Halo Top ice cream. But, yeah. So, yeah.
Sorry, what's the reaction going from alkene to an epoxide directly?
We'll cover her in a minute.
Oh, okay.
Yeah, she's one of my favorite reactions.
Cool.
Ding dong. We'll get to her. So, this is a skill builder, and I want you to try it out with the anti-addition. And one thing to notice is we're not doing it with just Br2, Cl2. We're doing it with I and Cl. And so try to think through which side are we going to attack. My little second hint after the electronegativity is hint. Antibonding orbitals are larger on what lobe or what side? So be thinking about that. But then also, because this is kind of a quick question, I'm going to draw a second question for you to try out that is just one that I made. So we ready? Let's see. Okay, so in an antibond, do we place the larger lobe on the more electronegative element or the less electronegative element? The less, because in the bonding orbital, this sigma bond is going to be lopsided to the more electronegative. So in the bonding orbital, it's going to be like, ooh, with slightly bigger on the chlorine side. That wasn't great. Blue. And so for the antibond, we're going to have blue, bloop, bloop, bloop. So we're going to attack the lobe on the iodine. So first step, we attack the iodine, and we are going to kick off the Cl as a consequence because we're putting electrons in the antibonding orbital. But then in our anti-addition mechanism, we also have that concerted bit where the lone pair of the iodine attacks right back. So when we do that, what we get is a little triangle with an eye. So with bromine, cyclic bromonium. With chlorine, cyclic chloronium. Anyone want to guess what I is?
Iodonium?
Iodonium!
Oh my god.
Crazy stuff. So here we have this. And then don't worry about stereochemistry for right now because we'll see in a minute what happens. So now Cl is going to come and attack, and it attacks the more substituted side. So does it attack carbon 1 or does it attack carbon 2? 1. She's more substituted. She has more things on it. So attack, kick off. And what we get, should be an I. And we have a Cl. Now is this a stereocenter? No, 2 methyls. Is this a stereocenter?
No, hydrogens.
So there's no stereochemistry. We have one product. Love that. Love her. So we didn't have to really worry about wedges and dashes here because we're not forming a stereocenter. Just something to like be watchful of. One thing that some students do as well is like when they're doing like a rough draft of the mechanism for something like this is they would just make everything look flat and then go back and add the stereochemistry afterwards just to help keep it straight. But yeah, it's not going to matter because also neither of these are stereocenters. This has 2 hydrogens. This has 2 methyls. So you can draw it on wedges. You can draw it on dashes. Live your truth. Now this one's fun. So she's going to do the whole like forming the cyclic bromonium, which I'm going to assume that you can do like the arrows for that. Bloop. But now we do have one bromoboy around. We don't have water. But what else do we have? Another alcohol on the same molecule, which is kind of like doing a reaction with Br2 ROH, alcohol, where we added an alcohol and a bromine. But we can do this really quick intramolecular reaction where which side is going to attack the more substituted side, right? So, bloop, bloop. When we do this, we make a 1, 2, 3, 4, 5-membered ring, including that oxygen. And then I will do my numbering. So 1, 2, 3, 4, 5. Right now, this still has a positive charge on the oxygen. And then carbon 1 needs to have a dangly bit and a bromine. So 1, we have a dangly bit and a bromine. And so to get our final product, we just deprotonate this, which I'm not going to do the full arrows because I know y'all can do deprotonations at this point. We get her. Who'da thunk? Yeah.
Is one a stereocenter?
Yeah.
Totally is. Thank you. That's a great observation. It's a stereocenter here. So we would get this and we would get its enantiomer. Burke. Yeah.
Also, how do we know if it's a racemic mixture or not? Like if we would get the enantiomer.
Like, how do you know that you get both enantiomers, or how do you know it's racemic, like 50-50?
Oh, is that what it means?
Racemic technically means 50-50, but we don't enforce that super strictly, and we just assume if it can form both, it'll be about 50-50.
So when we have like, when we have a stereocenter, we can like do dashes, do we always assume that the enantiomer will also be formed?
For the most part, yeah. Mm-hmm. Work. And technically, if we're being really precise, we should probably do a plus minus in this step, because this right here, 1, 2, 3, 4, is a stereocenter. So we'll get the version of this on a wedge and a version of it on a dash. So good to be looking out for.
And we're just assuming the oxygen deprotonates.
Yeah. Yeah. It could be deprotonated by probably the bromo boy. Or it could be another molecule. Yeah. Work. So, we now can go on to so sad. Let's talk about alcohol. So, the issues. We need a reliable way for making whatever alcohol we want, because right now our only method up until this point has been this girl, and she can rearrange. Don't like that. So option 1, we have Markovnikov addition with some rearrangement. Option 2, what if we want to get the Markovnikov product with no rearrangement? We do mercury. You know, I think in the past I do normally have like a little box that covers all this, and I'm like, in this one, what happened? Rearrangement or no rearrangement? Markovnikov, random Markovnikov. But so sad, I forgot about her. So, if we want no rearrangement, we use HgOAC2 with H2O and then NaBH4. That's our second step. So that is our way of avoiding rearrangement. And then our way of doing anti-Markovnikov addition, where we add the OH on the less substituted side, also with no rearrangement, is hydroboration oxidation. So that's NaOH H2O2. And actually, the way I like writing it more is H2O2 OH minus, which I know we use Na a lot in this class. Like, it's okay if you put the negative charge, we won't count off for it. But the reason why I just do it rote is because in my first OChem 1 class, I memorized it this way, and I don't want to change it. So, H2O2 OH minus, and then second step, different classes call the second step different things, but for us, we just do it as, oh wait, I'm going backwards. Here we are. Good morning. Good morning. I meant the boron step. People can do different things. So we use BH3THF. But I put a whole infographic on more things for this reaction, like heads up, like you might see it as B2H6. This is what BH3THF together looks like, and there are different ways that we can notate it. But this is very much like for your own, if you're interested. Nothing on this box will be tested. It's just kind of like, So let's talk about these two reactions particularly, and like they are going to be very synthetically useful for us. Like if we need to make an alcohol from an alkene, we very rarely are going to use H3O+ because it can have this rearrangement. So oxymercuration reduction. The first step that we do is very, very similar to the halogen anti-additions here, where you have this concerted reaction where the pi CC attacks the sigma star HgO, and then that has a consequence arrow. If we broke this bond, we put electrons in an antibonding orbital, and then a lone pair on the mercury attacks back. Then we form a cyclic mercurinium ion, which is kind of like the cyclic bromonium and all of that. And then if we have H2O on our reaction arrow with the HgOAC2, then water is going to be the nucleophile that comes in and attacks the more substituted side, just like we saw with like the halogen anti-additions. Now don't like her. She's an organomercury. She's like one of those compounds that they say, if you get one drop on you, the scientists, one drop got on the skin and then she knew she was going to die. And she had like a week left to live and it was tragic. And it like scary stories. Like, organomercuries, no. So will y'all ever be doing this reaction? No. Well, especially now that lab is done for half of you. So congratulations on that. So when we do this, we still get our HgOAC and our OH added anti. But then our second step is we need to remove her and get back to like non-caustic land. Or not caustic, non-toxic land. So this NABH4 step, you don't need to know a mechanism for it because it's radical based. It is just going to replace the H2OAC with an H. This is Logan's infamous fake mechanism of just her. So the other thing with this is here we get a very distinct anti-orientation of these two. But then with this NABH4, it scrambles the stereochemistry. So sometimes this hydrogen that replaces it is going to add on the wedge where the HD was. Sometimes it's going to add on the dash. And so because of that, overall, we're getting mixed products of both a syn addition here, where like these are on the same side, and we're getting an anti addition where they are on opposite sides. Bert, when did I add the plus minus here? I think I did that because I realized it was missing in the answer when I typed it up. So please, on your version, write the plus minus because you will also get the version of this that's formed the enantiomer here. Because, and it all comes back to this first step, instead of forming on wedges, we could have had this on dashes. Work. Now, the slight variant of this is instead of H2O, if you have ROH and alcohol, then the thing that's going to attack here is ROH. And then suddenly you get an OR added over here after a deprotonation. So it varies it just slightly, but it's a way to add Markovnikov, just an alcohol here to make an ether. There's a really so I have bad mnemonics for both of these reactions and the way that it makes sense to me. So I think about Mercury, the gods, the Greek Roman gods, all of this, and how do I get a no rearrangement? I pray to the gods. Mercury, please make sure that there's no rearrangement. And then the gods, they like to mess with us a little bit, and that's why they scramble the second step. And we get a mixture of syn and anti. So dumb, I know. The next one's even worse. So this is oxymercuration reduction. Hydroboration oxidation, HBO for short. This is the worst mnemonic I've ever come up with, which is, has anyone ever heard of the movie John Tucker Must Die? Seminal early 2000s classic of this guy John Tucker is cheating on these girls and they realize it and then get revenge. It's a movie. In John Tucker Must Die, they are anti-John. And anti-John, they might be anti-Mark. Anti-Markovnikov. Where can you watch John Tucker Must Die? On HBO. So I go anti-Mark, anti-John. John Tucker Must Die, HBO, hydroboration oxidation.
It might be easier to just remember the thing on Facebook.
Or other things.
I think that it might be easier to
See, this is the one where I'm the students will lose respect for me in this section.
It's
Just
going to
memorizing
do it
another
change your
sequence of
services.
things. Yeah.
The thing is, I need to check if it's still on the HBO, because if not, it would be really funny.
I think to say it is wrong with the association probably happens actually very quickly.
Again, in my head, it's super clear. There's no other way, it could be, of
I want to
course.
say hydroboration oxidation must die in the exam, and it's that's nothing.
HBO Must Die.
I hate to say it's on Netflix.
Wait, no, it's not on any of them.
Really?
No, it's
Wait,
not.
this says it's on Netflix.
Wait, I'm not seeing.
Anyway, that's the mnemonic, and we're just going to imagine that's on HBO. And we all know this movie, John Tucker Must Die, Anti-John, Anti-Mark, Anti-Markovnikov, addition of the alcohol. So,
Netflix
this has
says it
2
actually-
steps.
Netflix says that you can do it, but then when you open it, it's not actually there.
It might be an international thing.
Yeah. So yeah, you can.
Anyway.
So,
You can
so, so,
buy it
so,
for $3.79 on Google Play.
the mechanism is we are going to have the pi CC go and attack the empty 2p orbital in the boron. And then we're going to have a concerted mechanism here. It's a little bit different. Now the sigma BH bond is going to attack the pi star CC. So it happens all at once. And again, imagine we are a double bond here, and then BH3 floats in from above. Then we're adding both the boron and the hydrogen on the same face because that's where that molecule floated in on. Or we could add it if BH3 floats in from below and our alkene is here, then we add like BH2 and H both on the bottom. It's going to be syn either way you cut it. So that is the stereochemistry of this one. It is syn. And then this step right here technically is Markovnikov. So between boron and hydrogen, boron is less electronegative. Hydrogen is the more electronegative. And we see hydrogen adds to the more substituted side. So if our definition of Markovnikov's rule, most electronegative thing adds to the more substituted side, this follows Markovnikov's rule so far. So then we have to trick the system. And when we trick the system, in step 2 here, we are replacing BH2 with an OH. And now, overall, if you didn't know all this happened, and you just looked at this and you said, the hydrogen's on the more substituted side, the OH is on the less, does this overall look Markovnikov or anti-Markovnikov? Anti. So we call this whole reaction together an anti-Markovnikov reaction, even though it technically follows Markovnikov's rule for this step with the alkene when we are adding. But generally speaking, this is our go-to method for making an anti-Markovnikov product. So I'm going to let you try out practice 3 here. So in the first one, you're just doing a mechanism for the oxymercuration reduction. And remember, second step, you don't need curved arrows. You can just do like NaBH4, and then that will get us there. This one also, you do not need to account for stereochemistry because we didn't put stereochemistry in the product. And then pay attention that this is a CH3OH, so an alcohol and not water. Then for this second one, you are going to be doing BH3, like hydroboration oxidation. But now you're doing it with deuterium instead. So be thinking about what adds in each step. Is it a deuterium or a hydrogen? And in the second step, you have your normal oxidation. And then the last one, I think is part of a challenge problem, maybe, which is just doing a short little synthesis of like a few steps of how do we get a bromine over here. So a few minutes to try it out, work on it, and then we'll go over it. talking about it. So the first one, I wrote in the mechanism already. I'm going to be writing in the second one while you check the first one. So here, we attack the boron. This attacks back.
I have a question about the first one. Wouldn't that be a stereocenter?
It would, but we didn't indicate any stereochemistry, so you don't have to account for it. Yeah. So this is a stereocenter. Technically, you would get plus minus. Yeah. Then for this one, we add the deuterium to the more substituted side here, because between deuterium, which is like hydrogen, and boron, the deuterium, like hydrogen, is more electronegative, adding to the more substituted side. But then step 2, which we don't have the mechanism for, all it's going to do is replace the BH2 or BD2 with an OH. So what we wind up with is we have a deuterium added here, and we have an OH added here. Now, is there any stereochemistry? Is this a stereocenter? No, because the ring is the same on both sides. Is this a stereocenter? No. Great. We'd love to see it. Then here. So you did learn a reaction that can do this in one step with radicals in lecture, but she's actually going to be really messy if we try to do this, because she's next to this like strained ring. And so if you try to use radicals with this, we're actually not going to get this product because the ring is going to expand. Again, we'll talk about radicals in section 9. But here, does it look like we've added a bromine Markovnikov or anti-Markovnikov? Anti-Markovnikov. What's the only reaction we've learned up until this point that's anti-Markovnikov? Anti-Mark, anti-John. John Tucker Must Die on HBO. So we use BH3, THF, then H2O2 OH minus. With that, the two things that we add are an OH and an H, and we add anti-Markovnikov, no rearrangement. And then we need to replace an alcohol with a bromine. Where have we seen that? PBR3, lecture 7, making alcohols leave. Oh my gosh, they're all connected. I feel like the exam 2 is going to be like y'all are watching a TV series, and each episode focuses on different characters, and then they all come together. It's like this That's So Sweet Life of Hannah Montana kind of crossover. Yeah. So, yeah, they all know each other. They all go to the same school. So, this is the kind of making alcohols one. And now, I have one more practice here that's kind of related to all of these that I think we should do together. So, a couple of these, like there's one that we haven't talked about, which is if we use like H2 palladium on carbon. It's one that you don't need to know a mechanism for, but the basic details of it are H2 palladium on carbon adds 2 hydrogens. When it adds 2 of the same things, I put Markovnikov, because like there's not a more electronegative one. So it's like, bad question. Don't ask me if it's Markovnikov or not, but also just to think about it as not an extra thing to memorize, be like, Markovnikov, basically. This is one that you don't need to know a mechanism for, but we do know that it's going to be syn, because they're going to add to the same face. It happens on a surface of palladium, and so both the hydrogens are added to the same side of the surface. But this is actually a deceptively tricky question, and you will definitely have one like it on the exam, where we know that this reaction added 2 deuteriums. We know it added, quote, Markovnikov, and we know it added syn, just from seeing these reagents. And again, deuterium and hydrogen are pretty interchangeable for us. But with that, we know it came from an alkene, right? Like an alkene would do this. The question is, did it come from this alkene, or did it come from this alkene? Like, should our methyls here be on the same side or opposite side? And honestly, if you just wrote one of them, it would only be like a 2-point deduction. Like in terms of like if you wrote the wrong one and just don't want to deal with the mess that we are about to do, save yourself the strife, take the 2-point deduction. But I want to teach you how to do the thing that's a little bit harder. So in order to correctly predict what this starting alkene was as either the E or the Z version, we need to redraw and visualize this molecule to see our two things that we added be syn. There are several ways that you can do this. If you look up other versions online, they will show you different methods. The one I like is whatever two things you add, put them in the plane in the same direction. So you could write them like both going down like this, or you can write them both going up like this. And we need to rotate and redraw this molecule so that it looks like this with the deuteriums. So let's start with this carbon. The deuterium's already in the right spot, correct? So what we can do is keep the methyl on the dash, and we can keep the hydrogen on the wedge. Great. Over here, though, we've had to go from a down on the dash deuterium to a down in the plane. So what we're doing is we're essentially like rotating everything forward just a little bit. It's not like a whole 120 degree rotation, it's just a little 60 degree like bump. So it would be the equivalent of like, imagine this is the deuterium that's down and away. We just need to go boop. So from here to bloop, just in the plane. And do you see how this red one that's going towards you, that would be down on a wedge, when I do the bloop, it's still going towards you, but now it's just up on a wedge. So this methyl is going to rotate up on a wedge, and then that means that this is going to rotate slightly back for the ethyl. With me so far, as just redrawing from here to here. It's maybe not clear why we're doing this, but once we've drawn this so that our two things that we add are in the plane here, then our wedges and dashes will tell us what's going to be cis to each other on the original alkene. So whichever two things are on wedges to each other need to be cis in the original molecule. And same thing with the dashes are going to be cis to each other. So we need the version where the methyl and hydrogen are on the same side. So here, do you see how the methyl and hydrogen are on opposite sides? We need the version where the methyl and the hydrogen are going to be on the same side. So that's this both pink version. And then that's going to make the other methyl and the ethyl both on the same side. And so that's how we know that this was our starting material that made this product rather than the other one. It's a lot. I'm going to do it like a couple more with you guided, just to kind of see this pattern repeated a few times. So, next one, I2. What two things does it add to an alkene? Yeah. Now, the dihalides, is it a syn reaction or anti-reaction? It's an anti-addition. And then it's, quote, Markovnikov. Again, we're adding to the same thing, so it doesn't matter. So, what I want is I want to make sure the two things I add are in the plane, one up, one down. That's how they gave it to us, right? Like, we don't have to like rotate around a single bond here. We can just write, okay, this is going to be an ethyl on a wedge, a hydrogen on a dash. This is going to be an ethyl on a wedge, a hydrogen on a dash. So we have our anti thing that was added from the double bond. Then we have the two things on wedges. The ethyls need to be cis to each other. And then the two things on dashes, the hydrogens need to be cis to each other. So here we have the hydrogens cis to each other, and then we have the ethyls cis to each other. Now, let me see if I can do this. So imagine like here, the red ones here are the iodines that are like up in the plane, down in the plane. And then the blue ones are the ethyls coming out at you. What I'm doing, and this is going to look kind of weird, is imagining that these both came from a double bond. And if I fold them over, do you see how the two ethyls are cis to each other on the alkene that started here? The blue ethyls. And again, one more time. So here, the anti-orientation of our two iodines here in the red. And then here, these blues are our ethyls coming out at you. When I fold this back in, bloop, to make a double bond, then our two ethyls are going to be cis to each other. And the only reason we know this is what happens is because we know this reaction is an anti-addition. So we know how to fold the molecule to do that. Again, it's just this weird kind of stereochemistry skill that comes in this specific type of problem that you will have exactly one of on the test. So, do you want to try doing this next one on your own? Like, try for like 90 seconds a minute. Try to figure out, okay, does this add syn or anti? Redrawing it, and then seeing what should be cis.
Colton, do you like the triple berry freezer flavor?
I do. Bubbler is such a refreshing way to start the day. I like the peach one more though, but I still, the one time I went to Target, I did not see it.
Oh, I should have got a restock by now. I probably could.
Oh my gosh. So, you might still be working. Unfortunately, I do have to start talking about it. So, we have BH3THF H2O2 NaOH, or OH minus. What two things does this reaction add overall?
An H and an OH.
An H and an OH. Does it add Markovnikov or anti-Markovnikov? Anti-Markovnikov, because of your clever mnemonic, you know that. And then, does it add syn, anti, or mixed? This is the other thing about the mnemonic. What do they show on HBO? They show syn. HBO, she's the uncensored, they show syn, like S-I-N, but like also S-Y-N. So, mnemonic.
Wait, sin is in like a show?
No, like sinful behavior. Ding dong. So, it adds syn here. So we know that we need to put our OH and our H in the plane together. And you could do it both up, you could do it both down, whichever way you think is going to be easier to rotate. But then this one was an even harder one than the other ones I did with y'all because you had to rotate both sides. So this one was up and behind, and then here the H was on a wedge. And we just need to rotate that just a little nudge forward. And when we do that, we rotate this H from being up on a wedge to being down on a wedge. And then our ethyl gets rotated back a little bit. On this side over here, we want the OH to go all the way up and in the plane. So here, this is the easy one where you can literally just rewrite all of these in the other positions. So you can rotate the hydrogen to being in the plane, the ethyl to being the dash, and then the methyl to being the wedge here. You can rotate a full 120 degrees. And then once we have redrawn it, we see that the two things that are on wedges are the methyl and hydrogen. The two things on dashes are the ethyls. So we know that the ethyls have to be cis to each other because they're both on dashes. So we have this version. But honestly, it is so valid to see all of this work, be like, that 2 points is not worth it. I'm just going to guess, and I'll have a 50-50 shot. Live your truth. Like, again, it's one of the things that when I was in OChem 1 learning this, I didn't learn this skill because I said, simply no. Like, simply ooh. But we can talk more about it if you have questions at the end, but I do want to move on to touch on some of the complex alkene additions. So I'm going to try to speed run through this because this, the alkene things always take longer than expected. Bloop. I'm not going to talk about all of the complex reactions because there are a lot, and I personally find the carbenoids boring. Like, I think Carbene, she's cool, but like, I don't care about her business, I don't care about her friends, and they form these very like isolated reactions. So I'm going to teach you about the highest yield ones. First up, ozonolysis. Ozonolysis, you don't need to know a reaction, like mechanism. All you need to know is the line reactions, and we have two flavors. So both of them start off with first step O3, ozone, and then the second step is either DMS or H2O2. So we call DMS reductive conditions, and we call H2O2 oxidative. Oxidative, well, there's an oxygen in it. I don't know. You need a fake mechanism for how to do this reaction. What she does, I think of her as oxygen scissors. So she's going to go looking for a double bond, and then when she finds a double bond, she's going to cut it on either side, put an oxygen. So here we cut, and then over here, we now have a double bond to oxygen, and over here, we now have a double bond to oxygen. This was Logan's fake mechanism where he just erased it a little bit and wrote O's on either side. Boop, boop. So it is a really, really powerful reaction for like busting stuff up, like splitting things apart, especially like rings. If you go from something that is a ring in your starting material to explode it open, you probably did an ozonolysis. Like, it's the easiest way to bust open a ring. Yeah, I don't have a good mnemonic for it. I have another story for this reaction another time that's very embarrassing. But let's think about just doing some of these quick line reactions of how to bust it open. So for this first one, I cut in half, and I put a carbonyl on either side. And if you were in reductive conditions, the DMS version, you are done with your fake mechanism. You just cut in half, put double bond oxygen on either side. But if you have this H2O2 second step, you have to do one last thing, which is check, are any of them aldehydes? And if it is an aldehyde, then in your reductive version going to your oxidative version, you need to change the H of the aldehyde into an OH carboxylic acid. So they both have the same cut, add the double bond O, but then if you're in oxidative conditions, you take aldehydes all the way to carboxylic acids. So can you try out these two very, very quickly? I'm going to give you like 30 to 45 seconds. And I'm going to be writing my answers at the same time.
Do we have to chop up every single double bond?
No, so it only affects alkenes, not arenes.
Oh,
Arenes have a different reactivity. That's lecture 9 stuff.
Yeah, I chopped up every single.
Oh no.
God. Thought I was having a big brain moment.
What?
How do you know for an oxidative condition?
H2O2 is oxidative. Mm-hmm. How'd you do? So for this one, when we cut it, in reductive conditions, we have an aldehyde on this side and a ketone on this side. And then the oxidative conditions, instead of an aldehyde, you take it all the way to carboxylic acid. Ketones stay ketones. They don't get to a higher oxidation level. Now this, when you cut it, both versions are ketones. So the oxidative conditions and the reductive conditions are going to yield the same products. You could use either one and get the same results. Yeah.
If you draw them vertically, it looks like a sad person for the second one. If you rotate it 90 degrees.
If you rotate it 90 degrees.
No, the one above. Like, yeah.
He looks kind of happy.
Okay,
He
yours
looks
is
kind of
happy,
high.
mine is
Yeah.
sad.
Work. Okay. Cool. Moving on. Osmium tetroxide. So she's a way of making a vicinal diol where we've added 2 OHs on neighboring carbons. The thing I want to point out here is you have learned one other reaction to make vicinal diols in lecture 7. How did we make it in lecture 7? Epoxide. So we can make it from this bad boy with H3O+. You could also do it in like basic conditions depending on what you started off with your epoxide. Either one works. But the big thing is when you do the lecture 7 version with epoxide, it is anti. When you do the osmium version, it is syn. That's going to be important. There are going to be questions that engage with it. Now, what else could you do with a vicinal diol? I don't know. What could you do with a vicinal diol? Could you do like... What would this reaction be? I like this question. I like this question, and I write your exams. I like this question. And I think you'll see it on several practice exams. Like, that's not trade secrets. Then, epoxides. MCPBA. I just like her. I think she's neat. Yeah, you're able to do this peroxide reaction where you have 4 arrows in one step, and then she's done. She stands on business, then she gets out of town. It's my favorite reaction in OChem 1 because it's both easy and a little quirky. Yeah.
What did you say again? Sorry. Didn't write it down. What's the difference with the lecture 7 version of machines?
This is anti, whereas the osmium is syn. Mm-hmm. And then also if you're trying to make this kind of like acetal, you're going to want the syn version because anti, it would just be weird geometry to try to make a ring with that. Yeah. But last thing, speed run Wittig. The Wittig is going to be a very, very powerful reaction for making carbon-carbon single and double bonds at the same time. Like, and for this whole class so far, you know maybe 4 ways of making carbon-carbon bonds, especially sigma bonds. You are not going to learn a ton more. So it is a really, really helpful way to do the reaction. When you do the Wittig reaction, you react with an ylide. And that's this negative charge on a carbon with a positive charge on this phosphorus right next door. And this is a phosphorus ylide. There are other types of ylides. Specifically, it forms the Z alkene, which is kind of like abnormal. You typically would think you would put your big groups opposite each other. But it specifically forms the Z alkene. And also to let you know where I'm at, I'm going to take 4 minutes, if that's okay. Because we did start 3 minutes after. So sorry, that's going to go 4 minutes over. If you need to leave, leave. So one of the things that also is really helpful with this is it's an easy way of making terminal alkenes. Now, why is it hard to make terminal alkenes via E1, E2? And it is on the screen. Yeah, it doesn't follow Zaitsev rule. We could mess with it with like doing the Hoffman product with tert-butoxide, all of that. But the Wittig is just a much more reliable way to make terminal alkenes. So the Wittig is between our ylide, which it attaches these kind of carbon groups with the carbons at the base of an aldehyde or a ketone. So here, these carbons get glued to these carbons, where this was that carbon here on the ylid. So if you're trying to make a terminal alkane, then essentially you need one side of it to be a single carbon. So you can make that single carbon formaldehyde here, so just this carbon, 2 H's, and the carbonyl. Or you can make it a CH2 ylid of just one carbon. You can do it in either way. So the line reaction here, first we need to know how to make the ylid, just like we need to know how to make a Grignard. We take an alkyl halide, we add PPH3 and then N-butyllithium. The PPH3 does an SN2 attack here, and then N-butyllithium acts as really just a base, which is kind of weird because you're used to seeing lithiums do like nucleophilic attacks. Here she's just going to deprotonate, and that's how we wind up with our ylid. The mechanism for this, she forms a box, which I just think is cool. I'm not going to go beat by beat through it just because I don't think that's the best use of your time right now, but I really like this mechanism. You 100% will see the Vidic on exam 2, either as a mechanism or in synthesis. It's 100% happening. But the last thing, the thing that's really useful, is if you see an alkene and you think it was a Vidig, we want to be able to disconnect it back to an ylid and a carbonyl. So I'm going to do 2 really quick, and then if you want to try the last one, you can. So first thing, you cut along the carbon-carbon double bond. We need to make one side a carbonyl and one side an ylid. So let's do that. I'm going to just make this one the carbonyl first. And if this bottom part's the carbonyl, then this CH2 needs to be our ylid. So we have this plus CH2 PPH3. And we'll have the minus and plus here. So that's one option. Or we could do the other option. And on the bottom one, we make that our ylid, or we have the PPH3 attached, and a negative on that carbon. And on the top one, we have the CH2 that we put a carbonyl. So we have two versions of this here. Now, which one is better? In order to answer that, we have to think about how we make our ylids here. So in this ylid formation, do you see that we have to do an SN2 attack? So because we have to do an SN2 attack, we typically want our ylid to be less substituted. Like we want it to be kind of a primary ylid, or a secondary and tertiary gets harder. Because if you have a tertiary carbon here, can this do an SN2 attack? No. So here, you have a secondary ylid versus a methyl ylid. Which one do you think is better? Methyl. So this is going to be the preferred way of joining them. And with that, I think I will probably call it here. If you want to try out the other practice, in the annotated version, it'll have the disconnection and the connection. But thank you for coming to section. Hopefully this was helpful for some things. Sorry for speed running at the end. I will see y'all later.
Your iPad also has the weird glitch for when you're sharing, it always says it's 9:41 a.m.
So it's not a glitch, actually. It's like intentional.